We're going to do a tiny little bit on acids and bases. Okay, we're going to talk about acids and bases for maybe 3 days, and hopefully get a lab in there. But acids and bases is in chapter 14. Okay, so this unit that we're covering is a little bit of chapter 5, chapter 12, and a little bit of chapter 14. So you will have kind of a quiz / test over this little mini unit on Friday. Okay, Friday of this week. Acids and bases. Can anyone give me some examples of acids that we see in everyday life? Acids and bases are meant to counteract one another. Okay? Whatever an acid does, a base can undo. Right? And vice versa. So acids and bases are meant to counteract each other. Let's talk about some properties of acids. Properties of acids. Although I would never recommend that you taste a strong acid, what do some acidic flavors taste like?
Vinegar.
They taste sour.
Vinegary.
Vinegary, okay, yeah. Acid in aqueous solution tastes sour. Aqueous? This is the abbreviation for concentrated. They are corrosive. Okay, if something corrodes, that means it means it wears away, right? It burns away. So when we have concentrated acids, they can start to be corrosive. Okay, do acids have an effect on the pH level of a substance?
Yes.
They do. What do you think it does to the pH level? Acids lower the pH level. Another property of acids is that they conduct electric currents.
Oh yeah, because you can put like 2 things in an orange.
So some properties of bases. What do we know about what bases are used for? Most of the time cleaning, right? Soaps, detergents, things like that to use cleaning. Yeah, and Tums, okay? So what's the taste of those things? Anyone ever gotten their mouth washed out with soap?
Pretty nasty. Depends on what it's called.
So bases,
Well, what
taste,
talking about bar?
either way.
I've had it.
Okay,
No, like,
bases taste bitter, okay? They have a bitter taste. It's the same thing if you're washing your face or washing your hair and some soap accidentally gets in your mouth, right? You automatically want to spit it out, right? It's gross, it tastes bitter. That's what the bases taste like. I'm never going to, again, suggest that you go ahead and taste bases, but the experience that we do have with them, and it gives us that bitter taste, okay? What about the feeling of soap when it's in water? What's it feel like?
It gets slippy.
Slippery, yes. Aqueous bases are slippery. Vinegar is an acid. Electricity. Okay, so bases conduct electricity as well. Okay, listen. What if when we're going to start, we're going to name with binary acids. What does binary mean? Binary means 2 things. What's one of the things have to be if it's an acid? Hydrogen and some other element, right? Maybe chlorine. Okay? So when we name this acid, it comes from a binary, right? It comes from an ide. And if it's a binary acid, we start it with hydro, and then we have whatever base it is, ends with ic acid. Okay, hydro, whatever it is, ic acid.
Hydroxic.
No, hydrochloric.
I know.
An acid that looks like this. What's it called? Hydrobromic acid. Hydrobromic acid. What if I give you, oops, hydrosulfuric acid? Give me the chemical formula for hydrosulfuric acid. HS? What's sulfide's charge? Negative 2, which means I need 2 hydrogens to balance that. Right? H2S. Acids always have to have a neutral charge, right? There can be no charge on an overall acid. Okay? So that's binary acids. Next is oxyacids. What's that mean? Yeah, it has an oxygen in it. Okay? There's 2 different ways that we name oxyacids. The first of which is if it comes from an 8 polyatomic ion, right? Phosphate, nitrate, chlorate, sulfate, right? Those come from 8 polyatomic ions. And what's the ending for the acid if it comes from an 8? Ic. Right? It's ic acid. Sulfate. Okay, and what is the chemical formula?
SO4 minus 2.
SO4 minus 2. So if I want to make this an acid, how many hydrogens do I need to add to that?
2. H2SO4.
2. So it's H2SO4. Okay, that is sulfuric acid. Yes, are we clear there? Okay, so what if I gave you phosphoric acid? Phosphoric acid. Give me the chemical formula for phosphoric acid. Perfect. H3PO4. Okay, because phosphate is PO4 minus 3, which means we need 3 hydrogens. H3PO4. Perfect. Okay, is this all review? Okay, yes. Okay. The other type of oxyacid comes from an ite. What's the ending for an ite acid? Good. OUS. Okay, so let's say I start with nitrite. Nitrite is NO. What is it? 2 minus 1. NO2 minus 1. So how many hydrogens do I need to pair with that?
1.
Okay. That would leave me with HNO2 called nitrous acid. Nitrous acid. Okay? This are you remembering this a little bit? If it comes from a binary acid, so if it comes from an ide, like sulfide or whatever.
Then it ends in
It goes hydro something ic. And it goes 8 and ite. All right, we were good with reviewing our naming? Okay, perfect. All right, next we're going to talk about something called strong acids and weak acids, and strong bases and weak bases. Okay, there's such a thing as strong and weak. So we're going to talk first about strong acids and bases. Okay, so for an acid or a base to be considered strong, right, a strong acid, it has to fit this criteria. And the criteria is that it ionizes completely, okay, or 100%. in water. Okay, it ionizes 100% in water. So we're thinking, what does that mean, right? What does ionized mean? Tell me, what does it mean to be an ion? It has a charge, right. So if I drop in an acid into some water, and I say it ionizes, what do you think that means is going on? It's getting a charge, so it's gaining or losing an electron. But does the molecule as a whole gain or lose electrons, or does it break apart? It breaks apart. That's what it means. It ionizes or it dissociates in water. So let's say I have nitric acid, HNO3, and I drop it into water, and I want it to ionize. That means I want to remove the cation and the anion from each other, right? So if it ionizes, it becomes H+, and it becomes NO3-, right? Those ions are separating. That's what it means to dissociate or to ionize. So a strong acid means that when it's dropped into water, every single one of those nitric acid molecules that I dropped in there is going to ionize. Every single hydrogen is going to be removed from every single nitrate. That's what it means to be a strong acid or a strong base. It just so happens that nitric acid is not a strong acid. I chose a bad example. But there are 6 acids that are considered strong, and they do this every single time you put them in water. Okay, so if you look on page 474, okay, in your textbook, 474, there's a table that has the 6 strong acids listed. Okay, they have them listed in a chemical reaction form, so it's saying the acid plus water yields this. I just want you to have those 6 strong acids down. You don't have to put down the full chemical reaction. Okay, 474, I believe, in the top of 474. Okay, can anyone give me an example of a base? Yeah, straight from the book, I know. Okay, bases usually have hydroxide in them. That's a really good indicator that it's a base that has hydroxide, okay? So, strong bases, okay, they will completely dissociate in water as well. Okay, they will 100% completely dissociate in water also. Okay, so what it's saying is that a strong base adds all of its hydroxides to the solution. Okay, most of the time, bases are going to contain a hydroxide ion. Right? Calcium hydroxide, sodium hydroxide, potassium hydroxide. Those are all examples of bases. So when we're dissociating, that means that an example for KOH, right? If we're dissociating that, the cation is coming away from the anion. So it would leave with a potassium plus charge and a hydroxide minus 1 charge. Right? That means it's dissociating. Those two are separating from one another. Okay? One is a positive, one is a negative. Okay? So they're going to completely dissociate in water. We've got our properties of acids and bases. We've got the strong for each picked out. The opposite kind of a strong base and a strong acid is a weak, right? We have a weak acid or a weak base. A weak acid and a weak base are any substance that just doesn't completely dissociate in water, right? Anytime it's only 50% dissociated or whatever it is, that's to be considered a weak acid or a weak base. Okay? The way that they differentiate between weak acids and weak bases and strong acids and strong bases. So the difference between weak and strong has to do with the polarity of bonds between those two atoms, between the hydrogen and whatever it's connected to. It has to do with the polarity and the bond energy within that bond. We're not going to get really into that, but that's what it has to do with. Okay. We're going to talk lastly about acid and base theory. Okay, and what this means is that we're going to look a little bit more closely into how we classify things as acids or bases. Okay, and there are 2 main theories for classifying an acid and a base. Okay, one of them I identify with a lot because it just makes sense to me. The other one is a little bit more wraparound, but both of them are perfectly fine theories. They just kind of have different ways of thinking. Okay, so the first one we're going to talk about is called a Bronsted Bronsted-Lowry acids and bases. Okay, so Bronsted-Lowry, this is one method of classifying an acid or a base. Okay, and his method says it's an acid if it is a proton donor. Okay, a proton donor. Okay, so he's saying if this compound has a proton available to donate to something else, it's to be considered an acid. Okay, and vice versa, it's considered a base if it is to be a proton acceptor. Okay, so if we've got two compounds and they're interacting in an acid-base reaction, one of them is donating that proton, one of them is accepting that proton. Okay, so in every acid-base reaction, there's got to be an acid and a base, right? One of them is accepting that proton, one of them is donating that proton. When we talk about protons, do you know what is actually being traded back and forth?
The electron.
A proton in what form? Yeah, a hydrogen. Okay, a hydrogen atom, more specifically a hydrogen ion, is to be considered just a proton. Because if I look at a hydrogen atom, let's take a look at a neutral hydrogen atom. What does it have? One proton and one electron. If I've got a positive charge, what's that mean I'm missing? I'm missing my electron, which means all I have left is a single proton.
So your proton donor.
Yep, if it's giving away a hydrogen, that's its proton donor, right? That's the acid. If it has a hydrogen to give away, that's considered a Bronsted acid. Okay? Okay, and this is the one that I think makes more sense to me because we can see that hydrogen moving from one to the other. Okay, in an acid-base reaction, we could see that moving between those two things. But the other theory, which again is not wrong, it's not any better or worse, but the other theory is called a Lewis acid and base theory. Okay, and a Lewis acid, he considers it to be an acid if it is an electron acceptor, and he considers it to be a base if it's an electron donor. Okay, so both of these examples, both of these theories mean the same thing. It just is differing in how we look at it. Are we looking at the protons or are we looking at the electrons? Okay, and let me show you how they both mean the same thing. Okay, if I'm looking at, let me give you a different one. Let's say I'm looking at, what acid is this? Nitric acid. Nitric acid. Okay, so let's say that nitric acid dissociates. And that means hydrogen moves over, leaves, goes bye-bye. Okay, it gave away that hydrogen, right? It dissociated. It donated that proton to something else, right? It's a proton donor. So that would be considered a what? A Bronsted acid or a Bronsted base? A Bronsted acid, right? It donated that proton to something else. If we flip our mindset and we look at the Lewis set of theories, right? This nitrate went from being nitric acid to now just being nitrate with a negative charge. What did it do with those electrons? Or what did it do with that electron? It accepted an extra electron, giving it that negative charge, right? So either way, the same exact thing happened. We just look at it a little differently. One's focusing on the protons, one focusing on the electrons. Okay? I like the proton version better just because you can physically see the hydrogen kind of moving back and forth. It's up to you. Okay? But you will have to identify, is this a Bronsted acid or a Bronsted base? Is this a Lewis acid or a Lewis base? Okay, you got to kind of pay attention to charges and where the proton goes, things like that. Okay, does that make sense? You'll never have to do both in one problem, right? They're either going to ask you for Bronsted bases and acids, or they're going to ask you for Lewis acids and bases. Okay? Questions here? All right, very last thing I want you to think about in terms of Bronsted acids and bases. Bronsted acids and bases. If I have a nitric acid, and I have sulfuric acid, and I have phosphoric acid, Those are all acids, right? They all have hydrogens available to donate, right? Those are proton donors. How many hydrogens does this one have to donate? 1. How many does this one have to donate? 2. How many does this one have? 3, okay? So this is what we call a monoprotic acid. Monoprotic, right? 1 proton. What would this one maybe be called, the second one? Good, diprotic. And then it's got more than 2. What would we maybe call it? Polyprotic. Very good. Polyprotic. Okay, that's one of your questions uses those terms, and I want you to be a little familiar with what they mean. Okay, hopefully you could figure them out on your own. But that's kind of what that's saying. It's got more than 1, or it's got 2, or it's got 1 hydrogen available to donate. Proton.